Hi students, welcome to the third video lecture on transform analysis of LTI systems. In this lecture, we will discuss about AllPass systems. So that's the topic of discussion for this video. So AllPass systems, what exactly does it mean? Let's start with the definition of AllPass systems. We consider here essentially stable LTI systems. So a stable LTI system we consider and again, as we were doing earlier, the transfer function of rational transfer functions are of interest for us. So with rational transfer function, transfer function h of z, okay, is called AllPass, so that we call it as AllPass under certain conditions, that being if its DTFT, satisfies, if its DTFT satisfies the condition that magnitude of h of e power j omega is equal to a, for some value of this, a could take any, for some value of a greater than 0, okay, and all w values and all omega values, and for all omega values, okay. Let's relook at it again. So we assume that it's a stable LTI system, otherwise h of e power j omega itself doesn't exist, right? It should include the unit circle, right? And that should, AllPass system should have a constant magnitude across all values of frequencies. So the gain of all, once you pass a system through it, the magnitude of the frequencies in the output would be they will be uniformly scaled, okay. In some textbooks you will find out h of e power j omega, this constant of a being 1 is also quite common, okay. Again, it doesn't make any assumptions about how the frequency, how the phase of this frequency spectrum should be, okay. Why do we use these AllPass systems? There are particularly two key applications of this. We have already seen and discussed in the earlier lectures that you could expect some effect, like the phase getting affected. So this can be used as a phase compensators while doing the filter design. So the reason being, this keeps your magnitude of your frequencies, the gain of the magnitude of the frequencies being constant across all frequencies, and at each frequency it could be designed in such a way that you get frequencies that are closer to the desired frequency. So they affect only the phase of the signal and not the magnitude of the frequency spectrum. They affect only the phase of the signal, right? So they can be used, hence they can be used as, as compensation for undesired phase shifts, as compensators for undesired phase shifts, and or delays, okay. This is one key application. This would be in case we might not get an opportunity in this course to discuss about the filter design, otherwise if at all you are going to do it at some point of time later, that's where you would come across again these AllPass systems. There is another important application. They are useful in the theory of they are quite useful in the theory of minimum phase systems. They are useful in the theory of minimum phase systems. I will anyway discuss about minimum phase systems in the next video lecture, so I won't be talking much about at this point. We will again get back to this at that point of time. Okay, this is what it means by AllPass systems. It has a magnitude of this frequency spectrum is constant. In some cases they will consider it as 1, or it could have any value of a positive value, and being the magnitude of this frequency spectrum being constant across all frequencies. Okay, now what we will do is, let's take an example to understand it better. Let's take the one specific example of the transfer function being having a pole at 1 minus a into g. If you have a pole at a, this is how we were writing. Now for this to be AllPass system, its numerators should be z minus 1 minus a conjugate. Okay, let's spend some time with this example to further understand it in more detail. So let's first take the frequency response of this function. So let's take the DTFT of it, e power j omega. So replace z with e power j omega, that would give you e power minus j omega minus a conjugate over 1 minus a into e power g minus 1. So that would be minus j omega. Okay, to see why it is having constant magnitude, let's further simplify this. For example, you take e power minus j omega common in the numerator, that would give us 1 minus a conjugate into e power j omega, right? And let me write the denominator as conjugate of a function. So if you do that, this is nothing but a conjugate e power j omega whole conjugate. I guess by this time you are already comfortable with finding the conjugate for functions. So a into e power minus j omega conjugate will be a conjugate, and e power minus j omega conjugate is essentially e power j omega, because cos omega minus j sin omega conjugate is cos omega plus j sin omega, right? Okay, now you could see in the numerator, the function 1 minus a conjugate into e power j omega, its conjugate is there in the denominator. So now if you try to compute the magnitude of this function, anyway the conjugate of, so whether it is a plus jb or a minus jb, magnitude is same, so that gets numerator and denominator gets cancelled out. So all you need to find out there is simply the magnitude of e power minus j omega. Again, this is having a magnitude of 1 and frequency of omega. So this is nothing but omega 1. So thus the magnitude you could see of this function of this nature is 1, right? This is as far as the magnitude is concerned. So we have now seen the magnitude part. Let's take a look at the phase of this function. What would be the phase of this transfer function? How can we compute that? Again, let's take it from this expression, okay, as a rational function e power minus j omega common, whichever we have taken. So phase of h ap of e power j omega is equal to this again we discussed in the earlier classes. This is nothing but e power minus j omega phase plus, it's in the same thing, so phase of 1 minus a conjugate into e power j omega, and then it's there in the denominator, so that into phase of 1 minus a conjugate e power j omega conjugate. This is what we need to find out, right? So we already know that for this function, angle of phase of e power minus j omega is nothing but minus omega, and then for the second term and the third term being the conjugate of the second term, the phase simply becomes a negative of that, right? So first let's try to find out, let's simplify the phase of this. Let's take this out and compute its phase. So phase of 1 minus a conjugate into e power j omega, if I have to compute it, is nothing but phase of 1 minus let's take a as a equal to r into e power j theta we will take. So we are letting a to take any complex number. Of course, when theta equal to 0, that could be, that already represents a real number as well. So right, so that would be 1 minus a conjugate is r into e power minus j theta. So this is equal to 1 minus a conjugate r into e power j times omega minus t, correct? So this is nothing but I could write it as the phase of one real and imaginary part. Let me separate that. R times cos of omega minus theta, that's the real part, and then minus j times sine of omega minus theta, correct? And that would be equal to tan in real and imaginary part. I could write it as tan inverse of yeah, by the way, there is r here also, r times sine of omega minus theta over 1 minus r times cos of omega minus theta, correct? So let's substitute this value here, okay? That implies the phase of this AllPass system is equal to minus omega. Well, there is a minus, this angle would get negative, so there is again that would result in minus is already there is a minus sign, so that minus of minus would become plus, so you would get 2 times here, 2 times tan inverse of r times sine of omega minus theta by 1 minus r times cos of omega minus theta. So that's the phase value, right? We had a look at this given function, this magnitude, its phase, and now let's see its pole zero plot. That's what we would see now. Pole zero plot for it is what we are going to see now. Okay, let's start with the denominator of it. Okay, the denominator is 1 minus, the denominator of that is 1 minus a into z minus 1. We have been dealing with it for quite some time now. This is nothing but z minus a by z, right? Which means it has, this being in the denominator, the root corresponds to the pole. It has a pole at z equal to a, and also it has a 0, and that 0 is at z equal to 0. Now let's take a look into the numerator part. What's the numerator? G minus a conjugate, correct? So let me take here this, I could write it as minus a conjugate by z, right? Let me take that out. Then this would be z minus 1 by a conjugate, correct? So which means this is again in the numerator. That means there is a 0 at z equal to 1 by a conjugate, and there is a pole at z equal to 0. And of course this 0 at z equal to 0, pole at z equal to 0 gets cancelled. So eventually what it has is it has a pole at z equal to a and a 0 at 1 by a conjugate. So if you draw this out, the pole zero plot, this being unit circle, real and imaginary axis, this being 1. Suppose you have a pole at, let's say for this part, if you have a pole at if you have a pole at a, let it be this value, okay? Now a, for example, let a be p plus jq, 1 by a conjugate it has it. So that's, it has here, 0 is here, Okay, if the pole is here, 0 is there, and vice versa. And suppose that's the case. Suppose if it takes a real value, assume there is another value of a you are considering. Let's say you have a pole at 1 by 2, and that means it has a 0 at 2. So that's another, if this is the case, this will be the nature of these things. So what we could say here for sure is AllPass systems will have conjugate reciprocal pole 0 pairs. This is a very important thing. So that implies, see here, you notice here, if you have a pole at z equal to a and 0 at 1 by a conjugate, which is nothing but you are taking conjugate and then reciprocal of it. So, or you could start with 1 by a conjugate as your pole and you will end up with the a then. So, what you could say is AllPass, this is a very important property here. AllPass systems will have conjugate reciprocal, taking conjugate, then you are taking the inverse of it, reciprocal pole 0 pairs. This is a very important property, pole 0 pairs. Okay, and few more points here. Any multiplication of this h of z with any z power minus n naught, if you take it, still you could notice that z power minus n naught multiplication is nothing but you're delaying your signal, so that still will have a constant magnitude but would have an impact on the phase only. So anyway, that would still remain as an AllPass system. So let me write that point observation also here. So any multiplication of above HAP of z with not only you could in fact write a into z power minus n naught. This a could take any complex value, doesn't really matter. That is still that is still AllPass AllPass filter. Okay, that's another important observation, right? So before we move further, one more point to mention here is any concatenation of these filters, okay, would still result in a cascade of these filters, also would still result in another AllPass system. So what we would now going to see here is a general form of AllPass filters is what we are going to see now. So let's take a look into that, the general form of AllPass filters. Let's take a look into this. So a cascade of AllPass filters is also an AllPass filter. So that's a very important thing. So cascade of, because they simply gets multiplied in the z domain, right? A cascade of AllPass filters is still an AllPass filter. Okay, another point to note is if your h of z represents a real function, okay, if the impulse response is if h of z represents a real valued system, then you cannot have a single isolated complex pole or zero. It should have its conjugate as well. This we already had seen it in the earlier classes. So it has a complex conjugate pairs. It will have, if at all it has any complex poles or zeros, it will for sure will have complex conjugate poles or zeros, right? That's another important observation in order to write the expression, general expression for how this all-pass filter Z transform would look like. As we discussed, a constant factor, it could get multiplied. Assume that it has real poles of m underscore r is the number of real poles that you have. So k equal to 1 to mr, those were the real number of poles that you have. In the denominator, in the similar way, 1 minus dk into z, this is exactly the same nature of function which we considered in our example. And in the numerator, g minus dk conjugate was what we were writing, that being a real pole. This doesn't really matter now, you could put simply dk. Not just that, you have this rational function having complex conjugate pairs of poles as well. Let mc be the number of complex conjugate pairs of poles. So this would be equivalent to, again let's write here, 1 minus ek g inverse. Okay, there are pairs here. If ek is there, ek conjugate also will be there, into z minus, that's in the denominator. In the numerator, g minus ek conjugate, that corresponds to the first one in the denominator, ek conjugate, and the other one will be g minus 1 minus ek, right? This is the this is the form of the general form of all pass filters. Okay, yeah, that's the key concepts that are related to the all pass system. So with this, now what I will do is I will give you a couple of exercises to work it out. So what I would expect is, we will be very likely having it in the next few days, or if not in this week itself, we would be having in the beginning of next week one conference call. By the time, I would expect that you would be solving these exercises that have given, including this video lecture and the previous 2 lectures, and be ready with those answers to that, so that make sure, by that I can make sure that you have carefully gone through it and you are ready to clarify your question, any of your doubts. Okay, so yeah, I'll give a couple of exercises here in this video lecture as well. Let the first exercise be, earlier we derived here the phase expression when you have a simple real pole of z minus 1, g inverse minus a conjugate by 1 minus a into z minus 1. Now I would ask you to derive the phase expression for a complex conjugate pair. So what I would say here is, derive the expression, for phase value of an LTI system, with h of z equal to, I'm just taking this part here. Okay, just one pair is what I am considering here. This z minus 1 minus ek conjugate multiplied with g minus 1 minus e subscript k divided by 1 minus ek z minus 1 into 1 minus ek conjugate into z minus 1. This is the problem 1 for you. Okay, one more exercise to make sure you have understood the reciprocal, conjugate reciprocals, and what should be the case for real valued impulse responses. So that would be covered in this exercise 2. Okay, so what we consider is a causal stable LTI system is what we are going to consider here. A causal and stable, okay, all-pass system is what we are considering here. Causal and stable all-pass, of course it's by default an LTI system. LTI system with real valued, so we are mentioning here impulse responses real valued. So with real valued impulse response, okay, assume that it contains 3 poles. That's what we are giving, contains 3 poles, okay, and one of which is at, and one of which out of these, one of them is at z equal to 0.8. We are giving you the information of one pole here, okay. Now we are not talking anything about the poles further, but you are given the information now about the zeros of it. If h of z has zeros at, let's say, z equal to 2 times e to the power of j pi by 4, so you already know that this is a complex 0, okay. That's one 0 has been given here. With that, what is h of z? That's what you need to figure it out, okay. And you write the logic behind how you arrived at that, and write the expression for it, and also draw the pole 0 plot as well there for the corresponding one, okay, pole 0 plot. And of course you know that anyway ROC is anyway outside the outermost pole, okay. Yeah, with that we are pretty much done with the AllPass systems, right? In the next video lecture I will be talking about the minimum phase systems, right? Okay, that's all for this lecture. You go through it carefully, and if you have any questions you could post them in the comments of this YouTube video as well, okay. See you in the next video lecture. Take care. Bye.